Welcome back to Wood Engineering. I'm Jeff Barochko from Carleton University, and in this video we are going to go through a full beam design check for a lumber joist with a notch. So we're going to check all of the different things that we need to check. We're going to look at the moment resistance, we're going to look at the bearing resistance, we are going to look at the shear resistance, and we're going to check deflection on this. So there's 4 different parts. We might break it up a little bit into a couple videos depending on how long it takes, but this is basically the situation that we're looking at. We have a 2x10 joist. The joist is sitting on I-beams at either end, steel I-beams, and the joist is a bit too deep for the beams. So basically there's a notch cut out at either end so that the joist can fit within between the 2 flanges to bear on the bottom flange. So this is one case where maybe we would want to consider doing a notch cut in our beam. Okay, there is a whole set of identical joists like this spaced at 400 millimeters on center. There's plywood on top to form a floor, and that plywood is fixed to it's adequately nailed to the top of the joists. So this is all going to come into play when we determine our KH, our system effect factor. There is loading, dead load and live loads. This is some interior floor. The dead load is 2.2 kPa, the live load is 4.8 kPa, so that's a uniform load over the entire surface, and our joist is an SPF number 1 under dry service conditions. So we are going to go ahead and calculate everything. So let's take stock of a few important parameters that we will use throughout. Our beam spacing, as mentioned before, is going to be 400 millimeters. Okay. The span, I am going to consider the span for this to be from the center of the bearing over here to the center of the bearing over here. So that's going to be 3.5 minus 100 on either end. So it's going to be 3,500 millimeters minus 200 millimeters. And so the span that I'm going to use is 3.3 meters, and that's our L. Okay, makes sense. We are told that it's dry service conditions, so all our K factors, KSB, KSV, KSF, which is the one for fracture, shear, KSCP, which is our compression perpendicular for bearing, KSE, which is for modulus, and are all going to equal 1.0 because we have dry conditions and there's no treatment, so KT is going to equal 1.0 as well. Now, what about our system effect factor? So you may recall that we have system effect factor conditions, and let's go to the system effect factor table. System factor. Okay, so here's our system factor table. We have bending, shear, compression parallel to grain. We don't have in this question, so we don't have to worry about it. And bearing does not have any system effect factor. So for bending and shear, if I go to the system factor section in the standard 6.4.4.2 or 6.4.4.1, we can see, okay, so does it satisfy case 1? 3 or more essentially parallel members spaced not more than 610 apart. Okay, check. They're 400 apart, arranged so that they mutually support the applied load. Okay, so case 1 is okay, but maybe we can apply case 2. So let's take a look. So case 2, the joists, rafters, or studs are sheathed with plywood, wafer board, or OSB, minimum of 9.5 millimeters thickness. Okay, that's good. So we have 10 millimeter plywood in the question. So that is a check. And the second criteria would be sheathing or subfloor is attached to the members to provide minimum stiffness equivalent to that provided by 2-inch common nails at 150 millimeter centers at edges of the sheathing panels. And in the question, I've just said it's basically adequately nailed, and the reason I say that is adequately nailed for system factor. So both criteria for case 2 are met. So actually, we're going to be able to use the case 2 system factor of 1.4 for our bending and shear calculations. So for KH, for bending and shear, KH is going to equal 1.4. So that's great. Okay, so now let's look at the loading conditions. Yeah, why don't we do the beam properties first, actually. So we're going to do the beam properties. So, because we already have some properties here. So let's find all the material properties and list them out. Okay, so we are using SPF number 1, and it's a 2x10. Okay, so that is a, if I'm talking about a 2x10, I'm talking about a 38 by 235. And so that's my size. So let's put that in. So I have a B equals 38 millimeters. D equals 235 millimeters. So that's my base and height of the cross section. And my area gross is going to equal 38 times 235, which is 8930 millimeters squared. And then what is my S? So for bending, we need our section modulus. And since I have this table up already, I can see for a 2x10, my section modulus is 351 times 10 to the 3. Millimeters cubed. Okay, so then let's find our strengths. Okay, so first I have to find my grade category. This is going to be a structural joist and plank category because it's 38 by 235. So it's going to be fallen structural joist and planks, which is going to be table 6.3.1. And we're talking about SPF number 1. So I can pick out my FB is 11.8. My FV for longitudinal shear is 1.5. FC we don't care about because we don't have compression, but FCP, perpendicular to grain compression, we do care about because of bearings. So that's going to be 5.3. And we don't care about tension, but we will care about our E for deflection, and that's it. Yeah, so we need E for deflection, FCP for bearing, FV for shear, and FB for bending. So let's put those in here so that we have a record. So we have FB equals 11.8 MPa. FV is 1.5 MPa. FCP is 5.3 MPa. And our Young's modulus, which is our mean Young's modulus because we're looking at serviceability for deflection, is 9,500 MPa. Okay, then what about our net area? Okay, so our notch depth, say notch DN is going to be right here. It's given as 30 millimeters. Okay, that's the depth of our notch. And our E calculation is going to depend on whether we use the total bearing length or just the minimum bearing length, like the required bearing length. And we're going to cover that in a little bit. So I'm going to leave E out for now. But our DN is 30 millimeters. Therefore, our AN, our net area, is B times D minus 30, which is 38, 235 minus 30, and we get 7790 millimeters squared. Okay, so now we have our net area, which is the area of the cross section with the notch removed, which we're going to need for our shear. And then we should also check to make sure that our net area is at least we can check our net area. Our net area has to be at least 75% of our gross area, and also the notch depth has to be no greater than 25% of the total depth. In this case, those criteria are the same. So if I take my notch depth divided by my total depth, I get 0.13, which is less than 25%. So we're okay in terms of notch. So we haven't cut out too much notch. So we're good to go. Okay. So next, let's look into, let's calculate our loads, our moments and everything like that. Okay. So our loading. All right, so I'm going to look at these load combinations directly. All of our loads are down, so we don't have to consider the 0.9D case. We only have live and dead, so it's going to be clear which load combinations govern. It's going to be either load combination 1, which is 1.4 times dead load, or load combination 2, which is 1.25 dead plus 1.5 live. We don't have any other loads, so there aren't really any companion loads to consider. So this is a pretty easy case in terms of load combinations. So let's start with the first one. Okay, so starting with load combination number 1, we've got 1.4 is the 1.4 times D, so that's load combination 1. So 1.4 times 2.2 kPa times 0.4, which is the tributary width, which is the spacing between the joists, and I get a load, distributed load of 1.2 kilonewtons per meter. That's the line load. Okay, now I can do this because all of the loads are exactly in the same position. So that means that I can kind of apply my load combinations in this case directly to the area loads. But I can't always do that if my loads for my different specified loads, like my live and my dead, are in different parts of the beam, for example. But in this case, they're all in the same. So I'm just going to factor actually the area load. And then after that, I can calculate my shear and my moment, which WL over 2 and WL squared over 8. Surely you know those equations for a simply supported beam with a uniform dead load. And I get 2 kilonewtons per my shear, maximum shear at the end of the beam, and 1.7 kilonewton meters for the maximum moment, which is at the center of my beam. And let's do the same thing for load combination 2 now. Okay, so load combination 2, I now have 1.25 dead plus 1.5 live. I have to multiply that again by the tributary area to get the line load. Here's the tributary area to get the line load, and I get 4 kilonewtons per meter. Then I can calculate my shear and my moment again. Shear at the end of the beam, 6.6, moment at the middle of the beam, 5.4. And okay, so now let's see if we can figure out which of these load combinations is going to govern for shear and for moment. And we're going to look at that in terms of the KD. So I have KD1 and KD2 here. And what I'm going to do is I'm going to use that little trick to see if I divide by KD for each of the shear and the moment, which one gives me the higher value, load combination 1 or load combination 2. For example, for load combination 1, if I have VF divided by KD, I get 3.1 kilonewtons. And for load combination 2, if I do VF divided by KD, I get 6.6 kilonewtons, because KD is 1 in that case. Okay, KD is 1 for the second one because it has live load, and KD is 0.65 for the first one because it only has dead load, as we know. Okay, and if I do the same thing for MF divided by KD, up here I'm going to get 2.6 kilonewton meters, and over here I'm going to get 5.4 kilonewton meters. Okay, so I'm using that little trick that we learned just to try to figure out which of these load combinations governs by trying to take out the effect of KD by assuming that the strength of the MR and the VR are going to be linearly proportional to KD. So therefore, these ones are going to govern because they are bigger. So okay, so now that means when I do my strength checks, I'm going to use an MF of 5.4 and I'm going to use a VF of 6.6. And then I am going to use a KD, a duration factor that is associated with that load combination, which in this case is 1.0. Okay, the last thing I want to do is ahead of time, while I'm thinking about loads, is to look at what is the VF at D from the support. And this will be for when we calculate our shear. So we've seen here that this is the shear diagram. Okay, it's a straight line. This is 6.6. This is 6.6. The total length that we are assuming here is, what was it, 3.3 meters? Okay, and so if I go, yeah, 3.3. So then if I want to go D inwards from the support, I want to look at this case where D is 235. That's the depth of our beam, 235 millimeters. So I want to find basically what is the height of this here. VF at D equals question mark. How do I do that? I can use similar triangles. So this length here is 3.3 divided by 2, right, which is 1.65, right? And to here, it's going to be that minus 235. So it's going to be 1.65 minus, so this is going to be 1.415. A bit hard to see there. So then my heights and my lengths are proportional, right? Because I'm talking about similar triangles. So that means that 6.6 over 1.65 is equal to VF at D divided by 1.415. And if I rearrange that, I'm going to find that VF at D equals 5.6 kilonewtons. Okay, so this applies to this particular shear diagram. If I have a different shear diagram, then I will calculate VF at D, whatever it is, just by looking at the diagram to figure out what the VF should be. Okay, so now this is what I'm going to use for my longitudinal shear resistance check. All right, very good. And it's the same value on the other side because this happens to be symmetric. This is the same VF at D over here. Okay, so let us begin then with the actual strength checks. And I am going to start with moment resistance. All right, so for moment resistance, you'll recall we have this equation. So first I need to find my capital FB, which is my modified strength, and small fb was 11.8, kd is 1, ks and kt are 1, and our kh we decided was 1.4 based on a case 2 system factor, and we get that our capital FB equals now 16.5 MPa. Okay, so that's FB. S we already calculated. KZB is our size effect factor. So let us go to the size effect table. Okay, so we have a 38 by 235 beam, and we're looking at KZB here. So 38, 235, I have a 1.1. So KZB equals 1.1 from that table 6.4.5. And then what about KL? Well, you remember that KL depends on my aspect ratio and depends on my support conditions. Okay, so if we satisfy these conditions, compressive edge held in line by sheathing, the joists are spaced at less than 610, and our aspect ratio is less than 6.5 to 1, which is condition C under the lumber KL provisions, then we can say that KL equals 1. So what is our beam aspect ratio? B over D is 235 divided by 38. And that gives us 6.2. So it's less than 6.5. The other conditions are satisfied. Therefore, KL for this case is going to be 1.0, which is good. It's efficient use of the beam. Okay, our phi we have. So now we can sub everything in. So phi is 0.9. FB is 16.5. S, as we recall before, was 351 times 10 to the 3. KZB is 1.1 and KL is 1.0, and we get an MR of 5.7 kilonewton meters. And what was our applied MF? So if we go back to our loading here, we see that our MF was 5.4 kilonewton meters. So it's just less. This is a very efficient design. So this is greater than MF, which equaled 5.4 kilonewton meters. So our resistance is greater than our factored moment. So therefore beam is okay for moment. Okay, next, we're going to check bearing resistance. Okay, so, there's a couple approaches that we can take to this. I know what my bearing length is in the design because it's given in my geometry. So my bearing length here is 200 millimeters. That's the width of the beam sitting on the flange. So I can check what is the strength QR associated with that 200 millimeter bearing times the 38 millimeter bearing width, which is the width of the beam, and find a QR and compare that to my QF. But also for later, since I want to do a detailed shear check, for the notch shear, sorry, that includes consideration of reducing the bearing length to the required bearing length instead of the actual bearing length, then I'm going to try to find actually what's my minimum bearing length right now. And of course, if my actual bearing length happens to be greater than my minimum bearing length, then I'm fine. Okay. There's also two things that I have to check here. I have to check effect of all applied loads at the bearing surface. And I also have to check the loads applied near a support, because there is some distributed load that is going to be within D of the support location, and I'm going to check that as well. Okay, so what's my QF? My QF here is equal to VF at the support, which is 6.6 kilonewtons, which we already determined. Okay, so this is my reaction force. Okay, and I'm going to need and you're going to recall that QR is equal to phi. This is for effect of all applied loads, FCP AB KB, the bearing, KZCP. Okay, so I need to find all these things. So what's my FCP? Okay, well, there's no system factor for bearing because bearing is fundamentally a local phenomenon. I can't have multiple members resist the bearing for one member. That fundamentally doesn't make sense. So I just have KD, KS, KT, they're all one. So my capital FCP is just small FCP, which is 5.3. What's my bearing factor? Length of bearing factor? It's going to be 1.0. I mean, if I don't know the bearing length, if I'm doing a design, I don't know the bearing length, then I should probably just assume 1.0 to start. But of course, in this case, we are within presumably 75 millimeters of the end. I mean, this is a conservative assumption because we might not necessarily be within 75 millimeters of the end if we're only considering the inner portion. Okay, so that's just good assumption. And then KZCP is going to equal also 1.0 because the member cross-section is vertical. Remember that KZCP is intended to compensate for when we're loading on the flat. Vertical. B over D is less than 1.0. Okay, so we have all those things. So what I'm going to do is I'm going to set QR to equal QF and solve for area of bearing that we need, AB. So if I rearrange that equation, I'm going to get AB min equals QR divided by phi FCP KB KZCP. So I'm going to get 6.6 kilonewtons divided by 0.8 is our phi for bearing, 5.3 is our FCP, 1.0 and 1.0. Being careful that 5.3 is an MPa, so I should consider 6.6 should be newtons if I want to get my answer out in millimeters squared. So this is going to give me 1549 millimeters squared. So that's the minimum amount of bearing that I need. Okay, so I calculated that if I did 6600 divided by 0.8 divided by 5.3, then I'll get 1549. Okay, so then if I assume bearing on full width of the member, which makes sense because, I mean, the beam is sitting on a flange, so the full width of this member is going to be sitting on this flange, so I think this is a very good assumption. This is basically what we're given. So then my LB min, my minimum bearing length along the length of the member, is going to be AB min divided by the width, which is 38 millimeters, and I get 40.8 millimeters. Actually, let's just call that 41 millimeters. Okay, so I have 200 millimeters, but I only need 41. So when I go to calculate my shear strength for the notch shear, I can take advantage of the fact that I have a smaller required bearing length than my actual bearing length and calculate my E based on the center of that required bearing length instead, as I discussed in the shear video. Okay, so now we're going to do the check of load applied near a support. So far what we've done above is done the check for all applied loads at the support. So now we're looking at basically, we have loads in this area and within D of the support. So if my support is like this and this is D, I'm looking for all of these loads to either side of the center that are within D of the support. So this, this part of the distributed load would not be included. I have a bearing surface up on top that is this bearing surface. Okay, so that's my top bearing surface. And on the bottom, I have this bearing surface down here. So that's going to give me my average bearing area between the two of those. And then I'm going to be able to calculate QR prime, which is the effective loads applied near support. So let's go ahead and do that. Okay, so here's the length. Okay, so we have a certain length within D of the support. We have on the right side 235, which is D, and on the right side we have 100, which is basically the part that is just to the left here. So we have 100 on this side, and we have 235 on this side, and so between the two we have 335. Okay, so what is my QF for this? It's going to be my WF times the L support. Okay, so it's only the portion of the load that goes directly from top to bottom. So it's not the full reaction. It's only that load on the top that's within D of the support. We went over this in a lot of detail when we talked about bearing. So the WF here is my factored load, which was 4.0 kilonewtons per meter. That's the load on the top of the beam for load combination number 2, and this is 335 millimeters. So if I multiply those together and fix the units, then I'm going to get 1.3 kilonewtons. Okay, so obviously I'm going to have to put 0.335 meters into my calculator to get 1.3 kilonewtons. Okay, so that's the number that I have to compare to my QR prime. Okay, so let's assume the minimum length. So we're going to assume that we're using the minimum length on the bottom and the maximum length on the actual length on the top. So let's calculate AB prime. You recall is okay, so I took a conservative assumption, which was I used the actual bearing length instead of, I used the required bearing length on the bottom of 41 instead of the actual bearing length, which is 200. And on the top, I used 335, which is the actual length of the area within D of the support on either side. And so I have to check here that this is less than 1.5 times B times LB1, which equals 1.5 times 38 by 41, which equals 2323. Sorry, I've run out of room here. So therefore, I have to make my A prime B equal to this 2323 millimeters squared. Okay, so this is a very conservative assumption. So if I can satisfy this, then I'm going to be more than fine. Okay, so QR prime, the equation looks like this. 2/3 times phi FCP AB prime KB KZCP. And this is 2/3. My phi is 0.8. My FCP, if you recall, is 5.3. My AB prime 2323 times 1 times 1. And I get 6.6 kilonewtons, which is greater than my QF is 1.3 kilonewtons. So we are A-OK for bearing. And this one happens to be way greater than what's needed. So I think the effect of all applied loads is going to govern here. All applied loads was, also a factor of about 4. So perhaps similar. Okay, so that means that bearing resistance is fine. I think that I'm going to make a cut in the video here so that we can cover shear resistance and the deflection resistance in a follow-on video.